Hi once again, I'm Mateusz, I'm a software engineer from Sokół, and today I would like to talk to you about ZIO-Actors. So for the last few months, I've been involved in contributing to ZIO ecosystem, especially to ZIO-Nio, ZIO-Actors, and I would like to share with you the work we've done within the ZIO-Actors project. So let's start. So first, I would like to talk about the agenda. So first, we're going to look at the general outline of actor model, just to recall it in just 2 slides. Then I will move to also Akka to also recall it in 1 slide, the general API design. And then I will move to ZIO-Actors to show you the library design together with examples. And we'll try to spot similarities and differences to Akka. And then at the end, I would like to share with you problems you have to face while implementing your own actor system. So let's start. So the actor model was first described by Carl Hewitt in his paper from 1970s, where he described it as a set of actors communicating with each other that do not share a common state. And while reading this paper, we can recognize the features that we're currently using, for example, in Akka, like the idea of work delegation, where we spawn children actors and send messages to them, or some interaction patterns, like, for example, fire and forget interaction pattern, where we send a message to an actor and we do not expect any message to be sent back to us. So for the sake of simplicity, let's simplify our actor idea to such diagram. So for us actors will receive the messages, then actor will process the message, where within processing, actor can spawn finite amount of children actors or send finite amount of messages to other actors. And then after that, actor can update its behavior, and the whole process starts from the beginning, taking the next message from the mailbox. So that was the general idea. Now let's decide what we would expect from the API design. So for us, actors should have a defined message type. So we should be aware what kind of messages we can send to that actor, that this actor can process. Actors should also form a supervision trees. So we should be able to define some supervision strategies that this actor can apply in case of message processing failure to recover with given schedule, or maybe elevate it to the higher level in hierarchy of actors. And we also would like to have our actors to be location transparent. So we should not be aware whether we're communicating with an actor residing on a local node or a remote one. Now let's recall the Akka. So in Akka, we have the Akka untyped, so Akka classic, where we define the actors by providing the implementation for a receive method, where we define how to process each message. There is also Akka untyped, so typed actors, where we model this with a so-called behaviors, where the behavior has a type parameter, where we define what kind of messages this actor can receive and process. And while processing the message, at the end, we can apply a new behavior to be used. We have also an actor system, which governs over a set of actors. We can spawn new actors. And also we have access to multiple interaction patterns like fire and forget or ask interaction pattern. So let's move to the ZIO-Actors. But before we do this, I will also really quickly introduce the general concept of a ZIO. So ZIO is basically an effect type inspired by Haskell I/O monad, where we will be modeling our computations within effects. And here you can see the ZIO data type, which has 3 type parameters. The first type parameter stands for the environment. So what kind of requirements this effect has to be executed. The second one stands for the errors. So what kind of exception, for example, the effect might fail with. And the last one stands for the success. So what type of value will be produced in case of successfully completing the computations. And for more convenient use, we have an access to multiple type aliases. And I would like to also quickly explain them because I will use them extensively in this code. So, for example, an effect that has no requirements and can't fail will be a UIO. And for example, an effect that also has no requirements and might fail with a throwable will be a task. And there are a few more. Okay, so let's move to the ZIO-Actors. So first thing, what we've got is the constructor for the actor system, where we have to provide the name for this actor system and also optional configuration file if we don't want to use the default application conf from resource directory. And as you can see, this produces an actor system wrapped in task, so wrapped in an effect. Having instantiated actor system, we have access to few methods. So we have access to make, which can be used for spawning new actors, where we have to provide an actor name that must be unique within this actor system, a supervision strategy for recovering from errors, some initial state S, and the stateful, where stateful is basically a description of actor's behavior. And this results in an actor ref, which is basically a reference to an actor. And here in make, we have 3 type parameters, which are used in a stateful that I will explain in the next slide. There is also a select method for a local and remote lookup, and the shutdown for stopping the whole actor system with all its actors. Okay, so now let's move to the stateful trait. So we've got the stateful trait with 3 type parameters. First one is the R, so also the environment, so what kind of requirements the actor has to process a message. Second one is the S, which stands for the state. And F, so what kind of messages we can send to the actor. And while defining our own stateful, all we have to do is provide the implementation for a receive method, where within processing a message, we have access to current actor state, a message that we're currently processing, and the context, where context is basically a handle to the actor system that this actor belongs to.
It should make them red or something.
And within the context, we have possibility to spawn children actors or perform a local or remote lookup. And processing a message should result in a tuple, where the left-hand side of a tuple is a new state that this actor will be updated with. And the right-hand side is a message that will be sent back to a sender in case of ask interaction pattern. So you can see that with receive, we have one additional type parameter. So here, on the level of a protocol, on the level of user-defined messages, we will also define what will be the type of a return message in case of ask interaction pattern. This we will see in an example in just few slides. So the last part from the API design is the actor ref, so a reference to an actor. And here we've got access to interaction methods, so question mark, so the ask interaction pattern, and the exclamation mark, so the fire and forget interaction pattern. And there is also path to access actor's path. Okay, so we've seen the library design. Now let's look at some examples. So the first example will be the actor that we would expect to behave as a counter. So first we need to define the messages that we can use. So we need a reset for setting counter to 0, increase to increase it by 1, and get for retrieving the counter's value. And here you can see the type of a messages that will be sent back in case of ask interaction pattern for each message within the brackets. So basically, reset and increase are expected to be used as a fire and forget. As for ask, there will be only a unit returned. And for get, we will have an int, so the actual counter's value. So let's define a simple stateful. So we create a new stateful, provide type parameters, and implementation for a receive method, where all we have to do is pattern match on a message that we received and produce accordingly a tuple. So for reset, we're setting counters to 0, increase, we increase it by 1, and for get, we do not change the state, and we return the state on the right-hand side of a tuple. So let's create a simple actor with that stateful. So in a for comprehension, first we create a new actor system. Then we're spawning a new actor with a given name, some initial state, and the handler that we just created. And then we perform a chain of interactions with that actor. And this is taken from a test suite. So you can see at the end that we're checking whether the actor behaved as we would expect. And here, similarly to the default behavior in Akka, we have the guarantee of message ordering between a pair of actors. So that was the simplest first example. Now let's move to something a little bit more complicated, but still really simple. So with that API, let's build a simple finite state machine. So let's imagine a pretty simple FSM that can be either opened or closed. And here we have also a few transitions. And you can see that this finite state machine is not total because there is no cell transition for a closed state. So this is for a purpose, for example, to see how to fail processing a message. And that's the use of it. So we're going to see how to fail it and trigger recovery strategy. So let's start with it. So first we need to define the messages and the state. So what messages we need to be able to send? So we need an open, closed, and cell. Where for cell I put the string in the brackets because, for example, you would like to have some invoice or receipt returned for an ask interaction pattern. Then we need a sealed trait for a state. So we need it into either opened or closed. And then also we would like some custom case class for an exception for that cell message for closed state. So let's build such stateful. So again, we're creating a new stateful providing type parameters. And here also for the requirements, we have a console. So here you will see the effectful print lining that here will be performing. And all we have to do, again, provide the implementation for a receive method, and it will be as easy as can be. So we'll pattern match on a state that we're currently in, and then on a message that we received. So for an open state and open message, we basically do nothing interesting. We do not change the state. For a close, first we perform some print lining that we're changing the state. Of course, it's wrapped in an effect and chaining it with an effectful, producing a tuple that changes the state to a closed. And for cell, we do not change the state and return some message for ask interaction pattern. For a closed state, everything is pretty much the same, except for a cell message, where here we can fail processing a message with an IO fail, providing our custom, for example, sale exception that we defined. And this will trigger the recovery strategy that will, for example, rerun processing a message with a given schedule, or maybe escalate this failure to the higher level of actors. So we've seen how to create the simple actors, how to fail processing a message. So now let's see some simple supervision strategies, how to define them and how to use them. So here you can see that for defining our supervisor, we need to use some schedule. So here, for example, we're using the schedule recurs and plugging into the supervisor retry. There are also supervisor none if we wouldn't like any schedule to be executed, and retry with it. And then after creating such policy, we can plug it into the system make, where we're spawning a new actor, and this actor will use that policy for handling the failures. And here we can benefit from a set of comprehensive and composable schedules from ZIO. So we have, for example, the schedule exponential, schedule recurs, schedule delay, and we can compose them with a logical or logical AND. So here, for example, the schedule S2 will rerun the effect in an exponential manner, at most 10 times. Currently, we've got also the remoting support that I hope in future will be used in clustering functionality. And for remoting, we also require the configuration, of course, for defining the host name and the port number, and for managing internally. So here, for managing the configuration, we are using the ZIO-Config, also a great library within the ZIO ecosystem. And configuration for remoting in ZIO-Actors is pretty much the same as in Akka. So we need to define the host name and the port that this actor system will be bound to. So let's see this in action in some simple example. So let's imagine that on one node we will create an actor system and then spawn a new actor. And then on another node, we can also create a new actor system and perform a remote lookup with a select method, providing the absolute path to that actor. And that way we'll acquire the actor reference. And we can perform also the interactions with that actor. And as we have the location transparency, which I explained at the beginning, the interaction will be pretty much the same as with a local actor. Okay, so the next thing will be the persistence. So currently, we've also got the first iteration of a persistence functionality, where we have the basic writing and reading to the data store. And we still don't have the snapshotting support, which is also coming. And also we've got a support for two data stores, the Postgres that is backed by Dubi. And the second one is the in-memory used for basically for a test suite in ZIO-Actors persistence. So also, as it's currently work in progress, but I would like to share with you the API design. So here we'll be using a little bit modified stateful, an event source stateful, which's got one additional type parameter, which is ev, which stands for the event. So what kind of events will here be persisting? And while creating our event source stateful, we have also to provide the persistence ID that will be used here. And we've got two methods, the receive and source event, where the source event is basically a transition from a current state and given event to a new state. And this function is pure, so we're not performing any effects there, because it's also used for restarting a new actor and reading from a data store. And we've got a little bit modified receive method, where the return type changed. So here in the left-hand side of a tuple that we're returning, we'll have a command with a given event. And command can either decide to persist an event or ignore if we don't want to persist anything. And the right-hand side of a tuple will be a function from a state to a message that will be sent back to a sender in case of ask interaction pattern. And the state that we have access here as an argument is a state after performing the source event method. So this is a mental equivalent of then run from Akka persistence. So let's create a simple persistent actor. So let's modify a bit our actor from the beginning. So the actor that behaves as a counter, and let's make this actor a persistent one. So what we need to do is create an additional sealed trait for events that can occur. And we require the reset event and the increase event that will be persisted. So first thing that we do is provide the implementation for a source event method where we pattern match on an event and produce accordingly a new state that is 0 or increase the current state by 1. Then we provide the implementation for a receive method where we also pattern match on a message that we received and produce accordingly a tuple where we're here using the command persist with a given event or ignore. And here you can see in command persist increase event that the right-hand side of this tuple is using this state after performing a source event that will return, for example, the updated counters value to the sender. And this creates us a whole new stateful that can be plugged into the actor. And then this actor will persist and read from the data store accordingly to the application conf file, so the configuration that we are providing. Okay, so that was all regarding the library design with some examples. Now I would like to share with you problems you have to face while implementing your own actor system. And while doing this, I was looking a lot at the Akka internals. And the fun part was that one of the source code files warned me that I might encounter dragons there. So that was pretty fun, I think, to find in a Akka source code. Okay, so the first thing I will talk about is the serialization. So when user defines its own messages, and they are just case classes, sealed trait, we can serialize them just like that and send over the wire, there's no problem. But the issue arises when the user defined messages have the parts of actor system inside. So for example, we're sending an actor ref over the wire. And this is a problem because we can't do this the same way, because after deserializing an actor, the deserialized actor won't be able to communicate with its original actor system because it's on another node. So for that purpose, we need some kind of mechanism that when sending actor over the wire, the deserialized actor will be able to communicate with its original actor system. And for that purpose, we have some internal duality. So internal implementation of an actor ref is basically the remote actor ref and the local actor ref. And once the actor goes over the wire, it becomes a remote one. And for the very first version, we did it with Java serialization. And currently we're moving towards another tool for serialization. But I would like to share with you the Java serialization implementation. So let's first talk about the serialization. So a serialized form of an actor is basically a path to that actor. So what's sent over the wire is just a string. And when deserializing, the deserialized path to that actor will be plugged into the actor ref remote. And this actor ref will use the socket communication to communicate with its original host, with our original actor system. Of course, Java serialization is known to be slow and prone to attacks. So we're currently, as I said, moving toward other tool for serialization. And this in future will be covered by ZIO codec library, also within the ZIO ecosystem. And the last part I would like to talk about is a socket handling. So also regarding the remoting. So let's imagine that we have a multiple nodes with multiple actors communicating with each other, sending the ask messages and fire and forget. And for this purpose, we will have a lot of connections. And we decided to handle them with a non-blocking I/O, concretely the Java NIO, where within the Java NIO we have a so-called selector mechanism, where we are able to handle multiple channels with just one or few threads, where, for example, if in one channel we're waiting for data to arrive, the selector might decide to move this thread from current channel to another one where the data already arrived and is ready to be read or written to. And the great part of that was we didn't need to implement it with a bare Java API, because there is a great ZIO NIO wrapper for that purpose. Also a library within the ZIO ecosystem. So we've made it to the goals. So what are the goals for a current year? So as I said, we've got persistence within our backlog, currently work in progress. As I said, we've done the very first iteration, as we've got the basic persistence functionality with 2 data store supports, including the Postgres. We've got also the serialization on our list. We've got also monitoring. So we hope to, in future, have a possibility to monitor actors on a given node. And the last part that most people ask about, especially during the functional Scala in London in December, where I gave the very first version of this presentation. So the clustering functionality, and this will be backed by ZIO Keeper, so another library within the ZIO ecosystem. And as we did some drafts, the clustering will have a lot of features compared to the Akka similar ones. So definitely the basic cluster functionality for cluster events, also the clustering cluster singleton, the distributed data, definitely. And also in far future, but I still hope it will be there, so the cluster sharding. Okay, so that was all what I wanted to share with you. Thank you very much for listening. Also, thank you very much for letting me speak at LambdaConf Global Edition. So also, I would like to invite you to contribution to ZIO and ZIO ecosystem, also to ZIO-Actors, as it's still work in progress library, and there are a lot of issues, also the easy one to start with open source contributions. So thank you very much once again, and do you have any questions? Okay, so I will open the Zoom webinar. Okay, so I've got the Q&A and Zoom webinar opened. Okay, so which I should start. Can someone just introduce ZIO briefly? So I gave two slides about it, but that there is a lot of documentation on ZIO.dev website. There is a great introduction from the basics about the ZIO. So I would really recommend also looking at that. Okay, so maybe let's start with the Q&A. So how do we guarantee referential transparency in an actor system where you have actors X and Y respond to a given events in one order versus another? Or is there something I am missing that I would make such scenario impossible? So basically, as I understand, this is a question regarding this a little bit different ask interaction pattern. So this definitely differs from Akka, and as I talked about the ZIO-Actors in some meetups also here in Poland, also the remote one. So the most thing that here differs from Akka is this ask interaction pattern, where we're like directly internally fulfilling some promise that will be sent back to a sender. And I think that, as I said, this is work in progress. Library will see how it works out, I think. ZIO-Akka cluster for clustering. There is a wrapper for Akka cluster, and as I said, as we're currently moving towards ZIO keeper, it will provide the cluster functionality. So the clustering within ZIO-Actors will be provided from ZIO keeper, and it will be also written from like scratch, I think. So we won't be incorporating any Akka in ZIO-Actors cluster. Okay. Can I spin an actor off and on a fiber? Well, so you can start an actor and stop an actor. That's definitely so within so within the internal access to the context in actor, we have also access to stop that actor. So you can just stop it. And as I understand, we are not able to turn it on and off just like that. What is the performance of ZIO-Actors comparing to the Akka ones? So also we've got the issue for performing the benchmarks, but unfortunately we still haven't done it yet. So it's hard for me to really elaborate on the performance of ZIO-Actors. Can you please talk a bit about consistency? Are there any delivery guarantees in the system? So here, as I said, when we're sending a message, it's for example the fire and forget interaction pattern. We're sending a message and continue, of course, but we're waiting until the message is enqueued in some internal mailbox. So we're acquiring this message ordering when we're firing a few messages from one actor. So there are also an issue for example, managing it for remote actors to not be blocked on a wire, but to store it in the stub mailbox for acquiring this ordering. You asked about the delivery guarantees. So for remoting, the delivery guarantees, I think, are as covered as for the by the remoting support. So as I said, we're using the Java ZIO API for reading and writing from it. So I think when it comes to delivery guarantees, I think I still need to dig into this topic. Definitely. Are there plans for Cassandra as data store for persistence? Yes, definitely. There is a issue for that, I think. But as I said, for providing a given persistence data store, we need to provide the journal, and anything that fits the journal API can be used as data store. So definitely the Cassandra will be able to fit that. Is okay. So I should, I think, click answer live or something like that, or dismiss. Okay, so I forgot to click that. Works fine for me. Okay, so answered, guarantees, data store. Okay, so there is still the chat. ZIO is a library for doing async concurrent programming. It's like a better future promise with batteries included. Okay, so that's not the question. Okay. I think also asked. I run into a limitation of Java ZIO selector. I can handle only 64 channels. Have you encountered that limit? So I guess we didn't make that much tests or benchmarks to handle 64 channels. So I think it's still ahead of us. So once again, this is very still work in progress. And I think, as I said, this one is one of the easiest to start with, as it's pretty small still, and I think understandable as you're accustomed to the idea of actors, of the actor that holds a state that you can communicate with. So it's really easy to understand this high-level API that the ZIO-Actors is providing. And as I said, there is a lot of issues to polish, and as I said, pretty easy things to do. So once again, I encourage you to try. We're all available at our Discord for ZIO Discord for any help or feedback. Okay. Okay, so that's all, I think. I don't see any new questions.
All right. Well, thank you so much for that presentation. Applause.
Thank you.
Yeah, looks exciting. I'm excited to see the progress of this project. I hope you inspired some people to join the project and maybe pick up one of the outstanding issues. All right, thank you so much. I hope everyone will, join us next week for Morgan Thomas's talk, Concurrency in Haskell, with Streamly. Streamly is a really interesting Haskell library that tries to unify a few different concepts. So if you're interested in streams or concurrent programming, data flow programming, and of course, functional programming, then please tune into that talk, which will be May 19th, Tuesday at the same time. Thank you all for attending, and I will see you next week. Bye-bye.
Bye.